See. Do have that. Okay. Okay. We should be on chapter 4, correct? We already did what is energy, right? Okay. Okay. Conservation of energy. Today, we are going to find how can energy change from one form to another? What is the law of conservation of energy? How much of the work done by a machine is useful for work, and what is efficiency? Okay, so how can energy change from one form to another? Imagine you are sitting in a roller coaster car. A conveyor belt pulls the car slowly up the first hill. When you reach the top of the hill, you are barely moving. Then the car goes over the top and you race down the hill. You speed faster and faster down the hill to the bottom. You continue to move up and down through smaller hills, twists and turns until you coast to the end. Okay? During the roller coaster ride, energy changes from one form to another many times. All of the energy required for the whole ride comes from the conveyor belts on the first hill. It does work as it lifts the car and passengers up the hill. The energy from that work is stored as gravitational potential energy at the top of the hill. Before the ride is over, the energy changes from potential energy into kinetic energy and back again several times. In addition, a small amount of stored energy is transferred to the wheels as heat. Some energy also makes the air vibrate and creates the roaring sound. The energy changes easily from one form to another, but the total amount of energy always remains the same. Okay, where does the roller coaster car have the most gravitational potential energy? Okay, it would be at the top of the hill. Okay. Okay. On the figure, circle the location at which the roller coaster car has the least gravitational potential energy. Okay, so that would be the lowest part of the track. Okay, so that is going to be right here, okay, the lowest part, okay? All right, potential energy to kinetic energy and back. At the top of the hill, all the energy of a roller coaster car is potential energy. The potential energy slowly changes to kinetic energy as the car accelerates down the hill. At the bottom of the hill, almost all of the potential energy has changed to kinetic energy. However, the system has the same total energy whether the car is at the top or the bottom. The kinetic energy of the car at the bottom of the hill can carry the car up another smaller hill. As the car climbs the hill, the car slows down and its kinetic energy decreases. Where does that energy go? Most of it turns back into potential energy. At the top of the smaller hill, the car still has some kinetic energy along with some potential energy. The kinetic energy carries the car forward over the top of the hill. The process continues to the end of the ride. Potential energy and kinetic energy and back again. Remember that the initial energy for the ride came from the work of the conveyor belt. Okay, so that's where the energy started to lift the car. The roller coaster cannot climb a hill as taller or taller than the first hill without more work being done. Okay, so most roller coasters, if you go back up higher than what you were before, they still have a belt on it that pulls you up. So the car does not have enough energy. The car cannot glide on forever. If the changes from potential energy to kinetic energy were complete, the roller coaster ride would never have to end. Where does the energy go? Well, it transforms into other forms of energy, like we said, the sound, the heat, all of those kind of things. Okay, let's see. So why can't a roller coaster go on forever? Okay. Because energy changes to other forms such as sound and heat. Okay. All right, mechanical energy to other forms of energy. Imagine dropping a tennis ball on the ground. With each bounce, it loses height. Eventually, it stops bouncing. If no energy were lost, the ball would bounce to its starting height forever. Okay, if the ball stops bouncing because not all of the kinetic energy changes to elastic potential energy when it bounces. With each bounce, the ball loses some of its mechanic energy. Okay. So identify two forms of potential energy that, okay, so at the top of a bounce, the ball's kinetic energy is 0. All of its kinetic energy has been converted to potential energy. So at that one moment, okay, but it's a pretty fast moment. When the ball hits the ground, some of its kinetic energy is changed to sound and heat. That's why it doesn't come back up as high as what it did before. Okay, so two forms of potential energy that the tennis ball has. Okay, so it's going to have gravitational, I don't know why it does that, and elastic potential energy. Okay, so it's going to have both the gravity that pulls down on it and that elastic, that spring back, is going to be potential energy. Okay, on the figure, place a circle where the ball has both kinetic energy and gravitational potential energy. So there's a lot of points here that can have both kinetic energy and gravitational potential energy. Okay, any point along this point, it is moving and it hasn't touched the ground. Once it touches the ground, then no, it doesn't have the gravitational potential energy, and we're not going to be at the very top. So all of these points, besides the bottom and the top, have both gravitational potential energy and kinetic potential energy. Okay, is the energy really lost? When the ball bounces, some of its kinetic energy compresses the air around the ball, which makes a sound. Some of the kinetic energy also heats the ball, the air, and the ground. Sound and heat are forms of non-mechanical energy. In most cases, when it seems that an object has lost mechanical energy, the energy has just changed forms. Similarly, a moving roller coaster car loses mechanical energy as it rolls because of friction and air resistance. The energy is not lost. Some of it increases the temperature of the tracks, the car's wheels, and the air. Some of the energy compresses the air around the wheels and causes a roaring sound. The car's mechanical energy has not disappeared. Some mechanical energy has just changed to non-mechanical forms. Okay, graphing mechanical energy. Graphs are a useful way to show relationships between variables. The graph bar below represents data about the mechanical energy of the roller coaster. Okay, so this is the potential energy. Okay, so this would be at the top of the hill. When you come back down, you're going to have less potential energy, but a little bit of kinetic energy. Okay, So this is when you're going to full speed, and then you're going to climb back up, okay? At which location does the roller coaster have the most kinetic energy? Okay, that's going to be where there's no potential energy, so that's actually going to be C, okay? Okay. Use the steps to learn about the relationship between potential energy that is illustrated in the graph. Study the axis to determine the variables. Okay, well, we have location here, and we have total mechanical energy, okay? Identify the independent and dependent variables. Location is the independent variable because location does not depend on the energy, okay? Kinetic and potential energy are the dependent variables because the car's energy depends on its location. 3, examine the legend and decide what it tells you about the relationship of the graph. The legend indicates the mechanical energy consists of both kinetic and potential energy. 4, examine the graph to decide what the data tells you about the relationship between kinetic and potential energy. So the graph shows that the total mechanical energy stays the same. So notice total mechanical energy stays the same for all of them, right? An increase in kinetic energy produces an equal decrease in kinetic energy. A decrease in kinetic energy produces an equal increase in potential energy. Name 2 things about the roller coaster car that you cannot learn by examining the graph. Okay, so there's a lot of them. Okay, so we don't know the speed, right? We don't know the speed. You don't know velocity. You will not know momentum. Let's see. You don't know mass. You don't know a lot of different things with this kind of graph. This just shows you a relationship between the total energy, potential energy, and kinetic energy, okay? Okay. What is the law of conservation of energy? We've studied that before. The energy present in the roller coaster car at the beginning of the ride is present throughout the ride. The same amount of energy is present at the end of the ride, even though the energy has changed forms. The energy of a bouncing ball changes forms, but none is lost. The work done on a machine is equal to the work it can do. The simple observations are based on one of the most important principles in science, the law of conservation of energy. Simply put, the law of conservation of energy is that energy cannot be created or destroyed. In other words, the total amount of energy in the universe never changes. Energy may change from one form to another, but energy never disappears. So what does the law of energy, conservation of energy state? It basically says energy cannot be created or destroyed. Cannot be created So it cannot be created or destroyed. Mechanical energy can change to non-mechanical forms of energy such as heat, light, and sound. So heat, light, and sound are all non-mechanical energies, but that also is energy. Energy in a system may move to the surrounding environment, but the total amount of energy does not change. Energy does not disappear. Energy also cannot be created from nothing. The total energy in the system can increase only if the energy enters the system. Energy can enter a system by doing work on a system. Imagine a boy bouncing on a trampoline. His second bounce is higher than his first bounce. How could his second bounce be higher? Because energy cannot just appear from nowhere. He must have added energy by doing work with his legs. Okay, what are 2 kinds of energy that the chemicals in fireworks change into? Okay, when fireworks explode, chemical potential energy is converted into other kinds of energy. However, the total energy of the system remains the same. So there can be several things for this. It can be light, right? It can be sound because we hear sound, and it can be heat, okay? Because since exploding, it does give off heat, okay? Open and closed systems. Okay. If we had to include all the energy in the universe during every calculation, during energy calculations, the calculations would be impossible. Therefore, to make studying a process easier, scientists often limit their view of the world. They may decide to study only a small area or small number of objects. Scientists call such small parts of the universe systems. Okay, so this whole thing is a system, okay? Why is it impossible to consider all the energy in the universe when doing calculations? Well, there's just too much. The energy in the universe is too huge. Is too large. It's just too large. You just can't keep track of all of it, okay? All right. In a system includes a gas burner and a beaker, okay? A scientist could study the flow of energy from the burner to the beaker of water. There is also energy in the room from lights and heat. However, the scientist can ignore this energy because she has defined her system as the burner and the beaker. Okay, so the burner and the beaker is the system. Scientists describe systems based on whether matter and energy can flow across their boundaries. An open system is a system that can change both matter and energy. Okay, so an open system can exchange both matter and energy with its surroundings. A closed system is a system that can exchange energy but not matter. It cannot exchange matter with its surroundings. And an isolated system is a system that cannot exchange, so it cannot exchange either matter or energy with its surroundings. Okay, so how is a closed system different than an isolated system? Okay, so in a closed system, energy can move to its surroundings, but in an isolated system, both matter and energy cannot go to surroundings. Okay, thermodynamics and energy conservation. Okay, thermodynamics is the study of how energy moves during different processes. The process might be a bouncing ball, sanding wood, riding a roller coaster, or a plant converting sunlight to food. Thermodynamics can describe the movements of energy in each of these situations, okay? So thermodynamics is the study, and I'll make this larger here in a minute, the study of how energy moves, okay? It is the study of how energy moves. Remember that work can transfer energy from one object to another. You can lift a ball, you do work on it, the ball gains potential energy. Energy can also be transferred to heat. For example, when you place a piece of bread in a toaster, energy moves from the toaster to the bread. The energy causes the bread to heat up. In any closed system, a change in energy must be caused by work or heat being gained or lost. When no energy is transferred as work or heat, energy is conserved. This is the first law of energy of conservation. It's called the first law of thermodynamics, okay? Okay, so when no energy is transferred as work or heat, energy is conserved. Okay, that is the first law of thermodynamics. Okay, what is useful work? We use machines to make work easier, but only part of the work done by the machine is useful work. Useful work is work that a machine is designed to do. Okay, that's useful work. Okay, So useful work is work that a machine is designed to do. Okay. For example, suppose you want to raise the sail on a sailboat. You can raise the sail with a pulley, but you must do work against the force of friction in the pulley. You must lift the added weight of the rope and hook connected to the sail. As a result, only some of the energy that you transfer to the pulley is available to raise the sail. Therefore, only some of the work the pulley does to lift the sail is useful work, right? Okay, the pulleys on a sailboat can do work. However, like all machines, not all work they do is useful work. What happens to the energy you put into the pulley that is not used to raise the sail? Okay, so some of the work put into the machine or the pulley is lost to friction and other factors. So heat and everything else, because it's the friction and air will all be related. That's where some of the work goes. Okay. What is incidental work? Work that a machine does that does not deserve its intended purpose is incidental work. Think again of the pulley on the sailboat. This is friction between the rope and the pulley. The friction causes some of the work you put into the rope to change to heat. So that's where some of the work went. The heat does not help to raise the sail. So it is incidental work. Okay, that's called incidental work. In addition, some of the energy in the pulley causes air to vibrate, producing sound. So that sound is also another form of incidental work. Because of friction and other factors, only some of the work of any machine is applied to its intended purpose. The useful work done by the machine is always less than the total work put into it. Okay, so why is the work done by a machine always less than the work put into it? Okay. Because some work is lost to friction, heat, sound, so it cannot be as much as you put in, okay? Efficiency. So this is going to tell you how efficient, how much of your work is actually lost to that heat, sound, or friction. So the efficiency of a machine is how much useful work the machine can do. So how much useful work is going to do. Efficiency is the ratio of useful work to total work input. So here's the mathematical equation. Efficiency equals useful work divided by work input. Okay, so it's usually, and then we times it by 100 because efficiency is usually reported in percent signs. Okay. A machine that is 100% effective would produce exactly as much useful work as the work done on the machine. However, every machine has some friction, so no machine is 100% efficient. So you get that. No machine is 100% efficient. Because no machine is 100% efficient, all machines need at least a small amount of energy input to keep it going. Okay, that's why you have to constantly put energy back into the machine. People use machines to make work easier. Because of this, we must also put more energy into a machine than the machine can produce. The more efficient a machine is, the less energy we have to put into it. Therefore, scientists and engineers are always trying to design more efficient machines. If a machine were 100% efficient, how much work could you get out of it? Okay, so exactly as much as you put in. Exactly as much as you put in, okay? Okay, calculating efficiency. A student uses a ramp to lift 150 Newton box to a height of 2 meters. The student uses 400 joules of energy to push the box up the ramp. What is the percent efficiency of the ramp? The useful work output of the ramp is the work done on the box. You can calculate the work done on the box using the equation. Okay, so we have to find work first, okay? So work is the force times distance. So we know this is 150 newtons times 2 meters, because that's the distance. And we get work is 300 joules, okay? And the student we know uses 400 joules. So then we have to take 300 divided by 400, and we get 0.75 or 75% efficient. Okay, a sailor uses a rope on an old squeaky pulley to raise the sail. It takes 140 joules of work to lift the sail 1 meter. Using the pulley, he must do 180 joules of work to raise the sail. What is the percent efficiency of the pulley? Okay, so we know that the work that he did is 140 times 140 is what the work that he did. So it was 140, and we divide that by the work that he put in, which is 180 joules, and this is going to equal 0.78, which is going to equal 78%. We're going to work more on these math facts tomorrow. Okay, perpetual motion machines. Many clever inventors have tried to design machines that will keep going forever without any input of energy. Such machines are called perpetual motion machines. However, even with a lot of time and effort, no inventor will ever create a perpetual motion machine. This is because a perpetual motion machine can only work in the absence of friction and air resistance. These conditions are not found in our universe. Why are perpetual motion machines impossible? Because our universe has air and friction. Our universe has air, resistance, and friction. Okay? And so energy is always lost to those things. Okay? So today your homework is section 4 review, and I guess that's the only thing that you guys have is this section 4 review for today. Okay, and then tomorrow we will work on these other things. Okay, I am going to do attendance real quick again, and then I'll take, I just want to share base here. Okay, Emily Briggs, Jalen, Denise, John.
Here. I'm here.
Okay. First hour. Okay. Aaron. Sam. Torla. Lillian Geisler.
Here.
Sylvia.
Here.
Valerie. Sophia.
Here.
Mark. Alyssa. Megan Whiteley.
Here.
Zetseat.
Here.
Cedric. Theory. Antonio.
Here.
Nabika. Sally.
Here.
Sally. Kingston. Fode. Ericana.
Here.
Ryan. Raymond, Arosi, Morel, Keelan, Karina, Jaya, Star,
Here.
Maria,
Here.
Ashna,
Here.
Johnny, Azzy. Marley, Mason, Igor, Abby, Joycelyn,
Here.
Anders, Sylvia, sorry, not Sylvia, Hilda, Grant Villers, Nyla.
Here.
Okay. All right. Do I have any questions?